Next, I want to take a look at how we solve quadratic inequalities. And I want to talk a bit about the theory behind what we're going to do here before I jump into the examples. Now, when solving inequalities, you may remember linear inequalities are fairly straightforward. For the most part, we follow the same rules as we would for linear equations. The problem with quadratic inequalities is that doesn't work. We can't isolate the variable when there are multiple terms, for example, an x squared and an x term. So instead, the way we're going to handle this is if you think of what the graph of a quadratic equation, for example, looks like. It's a parabola, right? So it would look something like this. And this parabola, as it crosses the x-axis, basically jumps from being positive to negative, right? Like this, we'll do this in blue, this region up here and here, this is where the expression is positive. Y in that case would be positive. And this region down here is where the expression is negative. And the change is going to happen where we cross over the axis. So either, let's do this in a different color, either at this point here or this point here. So this is where the expression goes from being positive, where it's blue, to being negative, where it's green. Or on the right-hand side, the opposite happens. It goes from negative to positive. So the important thing here is if the expression changes sign from positive to negative, it happens at an x-intercept. And so what that means is if we can take the expression and determine its x-intercepts, we can then divide that x-axis into intervals. And we know on each of those intervals, it's either always going to be positive or always going to be negative. Now, how that pertains to an inequality is if we manage to set the equation either greater than or less than 0, then the interval where it's negative, that's going to correspond to it being less than 0, and the intervals where it's positive, that's going to correspond to it being greater than 0. Okay. I should point out that this little sketch here would be any random parabola, not necessarily the one in example A. So I don't want you to look at that and go, wait, that's not x squared minus 5x plus 6 or whatever. That wasn't my intention. Okay, so let's take a look at how this process works then. What we're going to do is take a look at the expression that's involved in this quadratic inequality, and we're going to determine where its x-intercepts are. We're then going to make a little table where we divide the x-axis into intervals based on those intercepts, and then figure out on which intervals is this thing positive and which is it negative. Excuse me. That will then allow us to figure out which intervals solve the inequality. The first step is going to be to move every term to the same side of the inequality. So what I'm going to do is subtract the 5x over to the left and add the 6 over to the left, and write this inequality as x squared minus 5x plus 6 is less than or equal to 0. Now what I'm going to do is factor that left-hand side, and this can fortunately be factored pretty easily as x minus 3 times x minus 2, right? Since negative 3 times negative 2 is positive 6, and negative 3 plus negative 2 is negative 5. And so that means that the x-intercepts for that expression on the left-hand side are positive 2 and positive 3. So again, I mentioned what I'd sketched out here on the upper right didn't necessarily pertain to this particular example, and we see now that's certainly not this parabola. Okay, but what we're going to do with this then is we're going to make a little table where we write out intervals using these intercepts, 2 and 3, as endpoints. So the first row in my table, I'm going to call the interval row. And I always want to start out at negative infinity and then go to the first x-intercept, in this case 2. Okay, and then in the next column, I'm going to go from that x-intercept to the next x-intercept, so from 2 to 3. And since that's my last x-intercept now, I'm going to go from 3 out to positive infinity. So what I've done is basically separated the real number line into intervals, where those intervals are punctuated by the x-intercepts. So they have endpoints of the x-intercepts. And again, you start from negative infinity and go to the first one, and then from the first to the second, and the second to the third, and the third to the fourth, and so on, until you run out of intercepts, and you go from that last one out to positive infinity. Okay, so next, what I need to do is pick a test value on each interval. And what I want to do with these test values is determine whether the expression, in this case x squared minus 5x plus 6, is positive or negative. on that interval. And the test value can be anything you want as long as it lies in this range. So from negative infinity to 2, the number 0 is in that interval, and 0 is probably the easiest number to use, so we'll go with that. From 2 to 3, unfortunately, there are no whole numbers between 2 and 3, and I can't use the endpoints themselves, so I have to get a little creative. I'll use 2.5, or you could write it as 5 halves if you wanted to use it as a fraction. Either one's fine. And then from 3 to infinity, we'll check 4. That's the smallest number on that interval. Smallest whole number on that interval, I should say. All right, and what we need to do with those test values is determine the sign. And when I say sign, I again mean the sign of this expression here, x squared minus 5x plus 6. And we're going to plug those test values we chose into that expression and see whether it's positive or negative. And we could use the factored form to do so. As a matter of fact, the factored form might be a little bit easier. If we check 0, x minus 3 times x minus 2, that's going to be 0 minus 3 times 0 minus 2. And the trick here is I actually don't need to figure out the value. I don't need to calculate the value here. I just need to know if it's positive or negative. And I know that 0 minus 3 is negative, and I know that x minus 2 is negative. So this thing is a negative times a negative, which means a positive. Now, it's simple enough in this case to calculate that it's positive 6, but for more complicated examples, this might save us a little bit of time, figuring out just the sign without actually working out the value. Okay, so 2.5, that was the next one, so let's try 2.5. If I plug that in for x, that's 2.5 minus 3 times 2.5 minus 2. And 2.5 minus 3 is going to be negative, since 3 is larger than 2.5. And 2.5 minus 2 is going to be positive because 2 is smaller than 2.5. So I have a negative times a positive, which means the result is negative. And lastly, let's check 4. I'm out of room up there, so I'll do it down here. 4 minus 3 times 4 minus 2. This is a positive times a positive, so that result is positive. All right, so let's look at the inequality here. We were looking for the values where this expression was less than or equal to 0. In other words, we wanted the values where it was negative. So that's going to be this interval here. So as far as expressing our solution is this inequality is going to be the interval from 2 to 3. And this means all the numbers between 2 and 3. Now, because equality is included, we wanted less than or equal to 0. We also have to include the endpoints of 2 and 3. And the way we're going to write that is by using brackets. So 2 to 3, that interval, this is going to include all the real numbers between 2 and 3 and also the endpoints themselves. When we use, and off to the side, when we use the parentheses, that's what's called an open interval, which means no endpoints. The endpoints aren't included. And then when we use the brackets, this is what's called a closed interval, which means the endpoints are included. Okay, so the reason I included the endpoints in this case is, again, our inequality said less than or equal to 0. So it equals 0 at 2 and 3. It's less than 0 between 2 and 3. All right, I want to take a look at another example. Now, in this case, the inequality isn't actually quadratic. It's an even higher degree. If we were to expand this out all the way, it would be a 4th degree polynomial. So this approach works for any polynomial inequality that's not linear. So not just quadratic, but cubic and quartic and so forth. Now, in this case, the left-hand side is already factored for us, which makes finding the x-intercepts even easier. The x-intercepts in this case are going to be 0, because that's where the first factor is 0, positive 1, that's where the second factor is 0, and positive 3, that's where the third factor is 0. So again, we'll make that same table where we separate the real number line into intervals, starting from negative infinity and going to the first x-intercept of 0, and then from the first x-intercept to the second, so from 0 to 1, and then from the second to the third, so from 1 to 3, and then the third one was the last one, so we can go from 3 out to infinity. We pick a test value on each interval. And again, you can choose different test values if you like. Between negative infinity and 0, I'll use negative 1. From 0 to 1, I have to pick a fraction because there are no whole numbers between 0 and 1, so I'll use 1/2, or 0.5. From 1 to 3, we could use 2, and from 3 to infinity, we could use 4. And then we use these to determine the sign. Now, shortcutting picking the sign is actually, it allows us to take some more shortcuts. This middle factor here, look at this x minus 1 squared. That factor is always positive, right? Because anytime we square a number, whether what we square is negative or positive, the result is going to come out positive. So when we're trying to determine the sign, and we're going to do so by first plugging in -1, that was our first test value, we have x is -1 times x minus 1, so -1 minus 1 squared, times x minus 3, so -1 minus 3. I always know that middle term, the square term, that's always going to be positive. So I have -1 is negative, times something I know is positive. -1 minus 3, that's definitely negative. So I have a negative times a positive times a negative. That result is going to be positive. All right, let's check 1/2. So x is 1/2. 1/2 minus 1 squared times 1/2 minus 3. All right, so 1/2 is positive. Again, the middle term, since it's being squared, is always positive. And then I have 1/2 minus 3, that's going to be negative, since 3 is larger than 1/2. So I have a positive times a negative, and that result would then be negative. Next test value was 2, so I have x is 2 times 2 minus 1 squared times 2 minus 3. So 2 is positive, middle term always positive, 2 minus 1 is negative, so I have a positive times a negative. And that result is then negative. And then finally we want to test 4, so x is 4 times 4 minus 1 squared times 4 minus 3. So we have a positive. For 4, we know the middle term is always positive because it's a square, and then 4 minus 1 is positive. So since all the factors are positive, the result here is going to be positive. Okay, so, sorry, let me go back up here for a second. Okay, cool. Oh, sorry, it was right here. I was looking for this. This thing is, so we're looking for where it's less than 0, so we're looking for where it is negative. So that's going to be those two middle intervals here. Okay, now in this case, since this was a strict inequality, just less than 0, that means that we don't want to include the endpoints. That means we have to get a little careful when we write our intervals. Our solution is going to be 0 to 1, and then also 1 to 3. Okay, but we're not including 1 and 3 and 0 and 1. That's why I'm using the parentheses for the open intervals instead of the brackets for the closed intervals. Now the way we put these two intervals together is we use the symbol here, which looks like a big U. And that symbol, let me put this in a box because this is our solution. But this symbol here, this U, is for the union. And the union means putting those two intervals together. So essentially what the union does is joins the two intervals. So it's saying we take everything from 0 to 1, not including the endpoints, and put it together with everything from 1 to 3, not including those endpoints, and that gives us our solution set for this inequality.